So, part 2, velocity and acceleration graphs. Lesson 4, part 1 was distance versus time graphs. Velocity versus time graphs is part 2. We will also look a little bit at acceleration versus time graphs, but really that starts getting into obscure calculus-y things, unless I keep them really simple. Motion, first of all, yeah. Oh, screen's still frozen like an idiot? Thank you. Let's try that. Haha. Motion, my friend, thank you, with several constant speeds. So we're going to start to ask, first of all, what if you have different speeds but you're not accelerating? And then eventually we're going to say, what if you have a changing speed? Well, average speed is the ratio of total distance to total time. Average speed is d total over t total. By the way, how do I know that this one here is speed and not velocity? Just by glancing at it. If it was velocity, what would I have done? Okay, that arrow notation. Just, again, I won't penalize you marks, but it's worth wrapping your brain around because there's a lot of information contained in that. And that's also, Justin, how you know this is distance, not displacement. Time is a scalar, so it's never going to have an arrow above it. Average velocity is defined in a similar manner. Oh, how can you tell that this is velocity and not speed? I stuck the arrow on there. It's going to be displacement over time, total displacement over total time. And you may recall, Thomas, I said to you, some textbooks will use the letter X for displacement. That's if you're moving horizontally on the x-axis, and I'm okay with that too. I think I told you the correct variable to use for distance is that, but that looks like 8 seconds and be 5, and it just gets yucky and confusing, so I'm not going to use that. But by the way, the reason it's an S is Sir Isaac Newton, who is one of the fathers of physics, did all of his math in Latin, and so the Latin word for velocity has an S, in case you're wondering. Example 1, find the average speed. Average what? Okay. For an object that moves at 6 meters per second for 4 seconds, and then 100 meters at 2.8 meters per second. I think this question has 2 parts. We're moving at 6 meters per second for 4 seconds. Then we're moving at, well, we're moving for a distance of 100 meters at 2.8 meters per second. I'm going to divide my page into 1, 2, 3 sections. The third section is where I'm actually going to crunch the answer. The first 2 sections is where I'm going to look at each part. And I think I gave you guys the acronym DFIC. When in doubt, DFIC, I list my data. I gave you guys the acronym DFIC, right? Data, formula. Okay. So for the first section, what do I know? What's this 6.00? What's that? How do I know it's not a time? Okay, so I am going to ask you to memorize units. That's worth doing. So I'm going to say V equals 6. You can put the meters per second if you want to, but I figure V implies that. What's that for? If I know V, if I know T, what else can I find? I think I can find that, right? Now, let's see here. We have V equals D over T. How could I get the D by itself? What's the T doing to the D mathematically? Adding, subtracting, multiplying, or dividing? Dividing, so how would I move the T over to the other side? What's the opposite of dividing by T? So I have this. D equals V times T. Much better than some stinking triangle. 6 times 4. I think I can even do this one in my head. 24. 24 what? Units. Meters. I always do it, make sure I got the right units in the question and at the end. Built-in error check. Okay. The second section, I see a 100. What's that? I see a 2.80. What's that? How do you know? You have to look at the next line and keep reading. Meters per second. Okay. You know what? I'd kind of like to find time. How can I find time? Well, let's look at this little equation right here. See the t? I'd like to get it by itself. What else is on the same side as that t there? What's the v doing to the t mathematically? Adding, subtracting, multiplying, or dividing? If we don't write anything, what's that the shorthand for in math? Multiplying. So I'm timesing by v. What's the opposite of timesing by v? So if I hear you correctly, Spencer, and I think I do, you're saying t is going to be the distance divided by v? You're saying I could divide it to that side? Yeah. Oh, do you see it? It just clicked. By the way, I'm going to really push this. This is called, Justin, formula manipulation. If I can beat this into you, and I will, it cuts down on your memorization so much. If I do my job right, by about Christmas, you'll look at complicated equations, formulas, be able to rewrite them in your head and get whatever you need to by itself. If I can get you there, it cuts down on your memorization. It's a great shortcut. And it's kind of also makes your little math nerd heart go pitter-pat, if I hope. Oh, Spence, you're on a roll. What's D in this part 2 section? 100. What's V? This one I can't do in my head. Well, maybe I can. It's going to be 50 divided by 1.4. Okay, it's going to be 25 divided by 0.7, which is the same as 250 divided by 7. 3.4. No, it's not 3 point. 30 point. Oh, heck, Dueck. What is it going to be? 35? So I wouldn't call that 35. If I was going to round off, what would I round that off to? Or 36. But you know what? I'll keep a few extra sig figs because this is not my final answer. This is not what the question wanted me to find. What did the question want me to find? Average speed, which is going to be in this third part, but I had to get some information from the 2 mini trips. So I'm going to write 35.71 seconds. Okay. We said is going to be total distance over total time. How far did we travel in the first trip? Plus, how far did we travel in the second trip? 100 over time. How long did we travel for in the first trip? 4 seconds. Plus, how long did we travel for in the second trip? Much longer, apparently. 35.71. Now, I'll write it this way. If you go to your calculator, is there more than one number on the top of the fraction? You'll have to put the top in brackets. Is there more than one number in the bottom of the fraction? You put the bottom in brackets. I won't write it that way because I think the brackets are implied. But on my calculator, which I'm sure all of you have out and are trying, 24 plus 100, close off the top. divided by, open bracket, 4 plus 35.71, close off the bottom. What was my average speed for this trip? Apparently about 3.1 meters per second. Not very fast, because that second trip, well, most of the time I was traveling at 2.8 meters per second. Jordan, for a little bit of time I was traveling a little bit faster, so my average should be a little bit bigger than 2.8, but still close to 2.8 because most of the time I was traveling 2.8. So that answer matches what I think the answer should be. What did I say it was? 3.1? 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 3.12. Units, meters per second. Example 2 says, sketch a graph of position versus time and velocity versus time. I'm going to pass on that because this graph is a bit of a yucky graph just because how many seconds elapsed in the first section? 4. How many seconds elapsed in the second section?
35.
I'd be drawing a graph that had one section 4 seconds long and another section 35 seconds. I didn't pick a good scale. I like the question for the contrast. I don't like the question for the graphing. So, next page. Instead, let's go to example 3. Here is a position time graph and the velocity time graph. And this is similar to how we opened up the class where I was giving you those scenarios, okay? And it looks like the key moment in time where something happened is right there. You know what? Let's kind of put a dotted line at about the same location. Eyeball it. That seems to be where something important occurs. So put a dotted line on the velocity time graph. Just about, by the way, did the dotted line print okay for you guys in the first graph? You can see it? Okay, because these are getting old. Is that okay, Madison? All right. Hey, what's going on? Don't put an arrow there. I'm just doing that. What's going on right there? Are we standing still, moving forwards, or moving backwards? And how do I know? Fast or slow? I need more information. Moving forwards. Are we changing speed in that section there? What would changing speed look like? Where does velocity or speed appear on a distance time graph? This was the key idea from last lesson. Oh, you're killing me. Oh. Where does speed or velocity appear on a velocity time graph? Come on, resurrect me, somebody.
On the y-axis.
No, it does not. On the y-axis is position. Did I say velocity? Position time graph. Where does speed appear? Where does velocity appear? I'm looking for one word, begins with the letter S.
Slope.
What?
Slope.
Say it louder.
Slope.
Bring me back from the dead.
Slope.
Oh, thank you. Slope. So if I was changing speed, what would be happening to my slope? Where does the speed or velocity appear on a position time graph? Slope. If I was changing speed, I'd have a changing what? Slope. So look at that. Is it a straight line, or is it a curve that's getting steeper, or a curve that's getting shallower? Back to you, Carson. Straight line, constant speed. Forwards, positive. You know what? It would look on my velocity time graph like that. Constant speed, positive. Thomas, could be higher or could be lower. I don't know because I don't have any numbers on here, but I'm telling you this graph would start out with a horizontal line above 0. What happens right here? This section of the graph. At rest. What would that look like? Now remember, speed on a velocity time graph is how high you are. If you're at rest, how fast are you traveling as a number? 0. So how high will you be? as a number, 0. You know what? It would look like that. That's the velocity time graph that matches this position time graph. And it did say describe the motion. Constant speed forward. How do I know forward? Because it's above 0. At rest. Is that okay? What does a constant speed forward look like on a position time graph? Positive constant slope. What does a constant speed forward look like on a velocity time graph? Horizontal line above the x-axis. What does at rest look like on a position time graph? Horizontal line. What does at rest look like on a velocity time graph? Also a horizontal line, but how high? Right along the x-axis, 0 high. Oh, hang on. No, I go till 11:55. Take that back. We can get one more done. Oh, you guys were all so excited. Ah, you shouldn't be excited. You should be disappointed. It's physics. It's fun. Ooh, in B, now I'm giving you the velocity time graph. And I'm saying, see if you can sketch the position time graph. You know what? It looks like this important dotted line is almost exactly halfway. So kind of eyeball the line pretty much halfway, I think, yeah? This seems to be where the action is. What's happening right there? Describe that motion. So I've heard at rest, no motion, constant velocity. One of them's right. Are we above 0, at 0, or below 0? Above 0, so we must be moving forwards. Steeper, horizontal, or shallow? That means my speed's not changing. Fancy word for that, yes, Carson, is constant forward or positive velocity. What would that look like on my position time graph? This? All lines are straight, Captain Obvious. Oh, you mean a line at an angle? Okay. How about like that? If you did your steeper, Thomas, I'd give you full marks because I haven't put any numbers on here. Steeper would mean I think it's going faster. I don't know. Maybe they're going up by tens. I don't know. But I would look for a line constant at an angle. What's happening right here? Are we above 0, at 0, or below 0? Constant velocity or changing velocity? How low is that line compared to the height of the earlier line? Are we going backwards faster than we were going forwards, slower than we were going forwards, or at the same speed as we were going forwards? Eyeballing it, it looks like it's not as low as the first line is high. So I'm even going to say, I think, so how will that translate into a line on my position time graph? How would I show backwards? Okay, don't write this down. Something like that. How would I show not as fast? Like this or like that? And you know what? I don't think, because I'm not going as fast, but I'm traveling for the same amount of time, I don't think I get back to where I started from. I don't think that this line would necessarily touch the x-axis again. I think when we stopped our stopwatch, hadn't got back yet. Now this is tricky, but you can see we can reason a lot of information from one simple graph. Acceleration is the rate of velocity change per second. I'm going to finish with this. Whenever we talk about the rate, what we really mean is divide by time. Acceleration is how fast velocity changes every second. It's meters per second per second. Except we never say meters per second per second. What we really say is meters per, you know what, you got two S's down there. Let's write it as meters per second squared. So the units of acceleration are meters per second squared, and that's also worth memorizing. When you see a meters per second squared, you know that's an acceleration, or if you find an acceleration, units, meters per second squared. You can also, we did do one example where we did kilometers per hour per second. I hate that unit. That's for cars, and you know what? I don't think I'm going to ever assess you on that. I did it on the sheet. I'm not going to throw it on a quiz or a test. That's ugh.